Hello and welcome to this calculus video. Today we will be talking about the derivative as a function.
Math 112.
In the last video, we defined the derivative of a function as a point. In this video, we are going to change perspective and try to take the derivative of a function f of x at all points simultaneously. Let f prime of x be the function that is equal to the derivative of f at the point x, if it is defined. F prime of x is itself a function called the derivative of x, and we can interpret it as giving the slope of the tangent line to the graph of f at the point x f of x. Let's compute a formula for f prime of x when f of x is x cubed minus x. By definition, f prime of x is the following limit, which we can evaluate by expanding the numerator and cancelling until it's written in a simpler form. After some algebra, we find the value of the limit is 3x squared minus 1. Let's take a look at the graphs of f of x and f prime of x side by side. As we see, where the tangent line to f of x is horizontal, f prime of x is 0. Where f of x is increasing, f prime of x is positive, and where f of x is decreasing, f prime of x is negative. Now let's try a second example where f of x equals the square root of x. To find f prime of x, we need to evaluate the limit that defines it. To do so, we rationalize the numerator, and this allows us to reduce the limit to a form we can do. We get 1 over 2 the square root of x. Notice here that f prime of x is not defined at x equals 0, while f of x is. Let's take a look at the graphs side by side. We see that the places where f of x is very steep corresponds to where f prime of x is very large in magnitude, and where f of x is shallow corresponds to where f prime of x is small in magnitude. There are many ways of writing the derivative of the function f of x. Some common ones include f prime of x, df by dx, and ddx of f of x. Also, if we let y equals f of x, then we can also write y prime or dy dx. Be careful to not treat d dx or df dx or dy dx as fractions. It is merely suggestive notation for a function that comes from the idea that delta y over delta x approaches dy by dx in the definition of the derivative. Let's take a look at one more example. F of x is the absolute value of x. Look at the graph of f of x, in particular the sharp corner at the origin. No tangent line exists here because the behavior of f of x changes abruptly. It can be shown that f of x equals absolute values of x has the following function as its derivative. Notice that it is not defined as 0, which means the derivative does not exist there. The derivative can fail to exist at a point for a number of different reasons. In this example, the derivative does not exist because the graph of the function has a sharp corner. Another key way in which a function can fail to be differentiable is if it is not continuous. Put another way, if f of x is differentiable at a, then f of x is continuous at a. We mentioned earlier that f prime of x is a function of x like f of x is. F prime of x can have its own derivative, which we denote f double prime x, or d2f by dx squared. As f prime of x measures the rate of change of f of x, f double prime of x measures the rate of change of the rate of change of f of x. We can also take more derivatives and get f triple prime of x, and so on. If f of x measures displacement of an object measured in time, then f prime of x is the rate of change of displacement, which is velocity, and f double prime of x is the rate of change of velocity, which is acceleration. That's all for now, folks. Today we talked about the derivative as a function. We described some alternate notations for the derivative and talked about some examples where a function is not differentiable at a point. We also stated a relationship between differentiability and continuity and introduced higher order derivatives.
Math 112.